Welcome to video 9 of Tensor Calculus. In this video, we're going to continue our analysis of vector differentiation. Only this time we're going to do it with respect to a coordinate system. This is going to lead us to the definition of a covariant basis and ultimately to the technique we use to represent vectors in Tensor Calculus. In our last video, we developed the understanding of the fact that the derivative of a position vector with respect to the arc length is just a unit vector tangent to the curve. You probably observed that we did all of that without the use of a coordinate system. Everything we did was based strictly upon geometric principles and ideas and geometric objects. Well, this time we want to throw a coordinate system into the mix and see where that takes us. So if we have our coordinate system z, which we use as a generic system in tensor calculus, we're going to start by parameterizing our coordinates, and we do it this way. We say that z1 is equal to a function of z1, and the argument of the function is the arc length. We do it for z2, and we do it for z3. Now I'm just going to do this whole example today in 3 dimensions. I think you'll be able to see by inference what it would look like if we extend it to higher dimensions. But for now, we're just going to do it as a 3-dimensional space. Now what we've done here is to assign 3 different functions, one for each of the coordinates, and each of these functions have as an argument the arc length. And that means as we move ourselves along this curve using the variable s to locate the point, every time we come to a point, such as P, we can use these functions to derive the actual coordinate values of the point, z1, z2, and z3. Okay, well now that we have that relationship, we can play the game that we've played a few times before, and that is to notice that r, although it is a function of the arc length, can now be expressed as a function of our coordinates. So r can also be expressed as a function of z1, which is a function of s, and z2, which is a function of s, and z3, which is a function of s. So again, as we've done in the past, we've created a composite function on the right. It's a little different this time, though, because the arguments are now, there are 3 arguments on the right, so we're dealing with a multivariable function on the right-hand side. Well, we'll take the derivative of this. Of course, this one is easy, dr ds. But on the right side, we have to use the chain rule. And if you remember your multivariable calculus, when we have multiple arguments like this, we have to start with the partial derivative of r with respect to z1 times the ordinary derivative of z1 with respect to s, and add similar terms for each of the other 2 coordinates. We take the partial with respect to z2 times ds dz2 ds, and then the partial of r with respect to z3 dz3 ds. And here we have the full derivative of this position vector with respect to our coordinates. We can simplify this a little bit. Obviously, the left side we know already is the unit vector. On the right side, we'll use the sigma symbol, which is traditionally used to represent summations. And so we can express these terms on the right as a single term. I will reverse the order of the factors here, and this time I'll use an index. And now the partial of r with respect to that same coordinate with the same index. And note that the index is going to vary from 1 to 3. So we now have a concise form for writing this expression. Okay, at this point I want to take a little detour and I want to introduce another concept to our tensor calculus syntax. You'll notice here that I have created a new index in the process of doing this. We now have this index called I. Of course, this should be no mystery to you. It's simply this index. But this is not a free index in our scheme of things. A free index was an index that appeared once in either the upper or lower position of every term throughout the expression, and the free index indicated multiple expressions. This is not the case. Here we have an index that appears in one term only, and it appears twice, once in the upper position, once in the lower position, and it represents an expansion to n different terms within the single expression that we're dealing with. So we call this kind of an index a dummy index. Now, Albert Einstein did a lot of work with tensor calculus and his work with general relativity, and he recognized that in the work you constantly wind up doing these kinds of differentiations, and every time you do one, you generate a set of n additional terms. You multiply the number of terms by n every time you take one of these derivatives, and he was constantly having to insert this summation sign, and he got pretty tired of it and realized that it really wasn't necessary. He recognized that every time this sort of thing occurred, he'd always get an index in the upper position and the lower position. There was always a pair of indexes, and it was always summed over the dimension of the space. So he proposed, and we have kind of used this convention, everyone uses it now, is just to omit the summation sign. So we would now represent this expression this way. We simply write down the factors dzi with respect to ds and the partial of r with respect to zi. And I see I missed something here. This was a vector, so let's correct that. All right. Now, the convention in tensor calculus is this. Just by inspection, you can tell that this expression has a dummy index. The fact that this index I exists here and here tells us it is a dummy index, and by implication, this is a summation. And we don't have to write that down. We understand it by the context of the expression. Okay, now to kind of drive that point home a little bit, let's go back and do the problem again. This time, I'm going to introduce a different curve. It's going to look like this. We have a path that comes from a different direction and sweeps in a different line and so on, but it passes through point P. And so this time, our vector r is tracing out the purple line and not the yellow one, although it does pass through the same point. So let's do this problem using tensor calculus notation exclusively. All right, so to start with, we would write this expression. We would say that zi is equal to zi, that the coordinate zi is equal to the function zi, which is a function of u this time. Now, because I'm using a free index, I have expressed all three of these expressions simultaneously. That's all I need to do, write it down one time. Okay, now when I get to this level, I can say that r, which was a function of s, this time it's a function of u, can be expressed as r as a function of z, which is a function of, keep doing the s, this is a u now. So this one expression means the same thing as this. You'll remember earlier we said that when we put arguments inside the function like this, that if we suppress the index, this is understood to mean the list of individual coordinates. So this expression means the same thing as this. Don't need to list them all out. And finally, because of Einstein's summation convention, we can now express the relationship of u hat directly by saying that is, first of all, dzi du times the partial of r with respect to zi. And we know by implication this is a summation. Here we have three terms, each of which have a factor of a scalar value and a vector value. This partial with respect to zi is a vector. So notice how the tensor calculus notation has simplified our problem. We can do in three little steps like this everything that it took us to do it in the expanded form on the left-hand side. All right, what do we have then? What you see is that the results are very similar. In fact, they're almost identical. The only difference between the two results is, first of all, the variable for our unit vector is different, and the variable here is different. Otherwise, the expressions are exactly the same. Now, in particular, what I want you to see is that each expression here is the product of a scalar value and a vector value. The derivative of a vector is a vector, of course. And not only that, but the vector in this expression is exactly the same vector as this one. What differs is the scalar factor out in front of it. What we've done in both of these cases is to express a single vector in terms of three different terms. This expands to three terms, and each term has a scalar times a vector, then plus a scalar times a vector, then plus a scalar times a vector. And doing that, what we have done is to decompose the vector into what we call a linear combination. Now, if you've had linear algebra, you'll understand that concept immediately, but even if you haven't, you're still familiar with it because you know that in the work that you've already done with coordinate systems, you know that you can take something like a vector v and you can express it in terms of some scalar quantity vx times a unit vector that goes along the x-axis in the coordinate system plus a y component times the unit vector in the y direction plus another scalar value in the z direction like this. This is also a linear combination. It's exactly the same form as this one. You take a scalar times a vector plus a scalar times a vector, etc., and the sum of these three terms equates to the individual vector. When we do this, we say that the vectors x, y, and z hat form what we call a basis. And a basis is simply any set of three vectors, or in n-dimensional space it would require n vectors, but three individual vectors that are linearly independent. Vectors are linearly independent if it is impossible to express any one of them in terms of the others. For example, we cannot express x hat here using a combination of y hat and z hat. Thus, x hat is linearly independent. Now, if all the vectors are linearly independent, it's impossible to express a zero vector unless all the vector components are zero. Thus, we have a simple test for linear independence. In this case, the only way to create a vector of length 0 is to set each of the individual components of the vector equal to 0 as well. Since that is the case, then x hat, y hat, and z hat are linearly independent, and thus they constitute a valid basis. Now I said all of that to make the point that this vector right here constitutes a valid basis. It is doing the same thing in a generalized sense that these vectors are doing in the Cartesian coordinate system. So we are now going to define something. We're going to define this symbol zi, lower index this time, and a vector quantity. We're going to define that as the partial derivative of r with respect to the coordinate value I. This expression, you'll notice it has a free index in it, so we're actually defining three things at the same time. And what we're defining here is a covariant basis. And the individual components that result from this definition are called covariant basis vectors. And by using this definition, we now know that we can express any vector in our space as a linear combination that looks like this. And we've now come up with a generalized way in which we can express a vector as a linear combination. Now, notice that our expression here is a general form of this. It works for Cartesian coordinates because z, I in Cartesian coordinates are just these values. So this looks like this in Cartesian coordinates, but it's also a generalized form that works in every coordinate system. And if you'll remember, that's what we're trying to do in the whole exercise in tensor calculus, is generate expressions, relationships that work in all coordinate systems. All right, well, this is a great stopping point. So let's take a break here and go do a quick review. The first thing we did was to introduce a new summation convention to our syntax. And that convention is this, that when we see an index in the upper position like this and in the lower position like this, both the same index in the same term, we recognize that as a dummy index as opposed to a free index. And the existence of such a dummy index when it comes in pairs like this implies a summation over each of the dimensions in our space, as is explicitly written out here. So the convention means that we do not need to include the summation sign. We recognize this itself as a summation just by the context. Okay, the second thing we did was to define what we call covariant basis vectors. The covariant basis vectors are simply vectors defined as the partial derivative of our position vector with respect to each coordinate variable respectively. Now I've written it down in the unprimed system and in the primed system to emphasize the fact that there's nothing special or unique about either one. We can define these things in either system. They're equivalent. All right, and finally, now that we have the covariant basis vectors, we can use them to create what we call linear combinations. Here we have made use of our summation convention. We have a dummy index, so we know that this expression means that we're summing over terms like this. There'll be n terms like this that we add together. There's a scalar value times a basis vector, and we'll add each of the terms that represent each of the dimensions, and we'll have a linear combination. So what that lets us do is to take this, which is a vector, being an invariant geometric object, has nothing to do with the coordinate system, but by using a linear combination like this, we now can decompose that vector into separate vectors, the sum of vectors, which makes it easy to analyze within the particular coordinate system that we're choosing to employ. In the next video, I'll show you what these basis vectors look like for each of our sample coordinate systems.